Okay, so here let's do this surface integral. So I'm integrating a scalar function, right? X squared z plus y squared z over the hemisphere x squared plus y squared plus z squared equals 4, with z being positive. So this is the top half of a sphere with a radius of 4. Okay, so it says a sphere, so I'm thinking that when I do this parametric surface, I should do something like spherical coordinates, which was, so spherical coordinates was, this is equal to rho um, sine phi cosine theta, y is equal to rho um, sine phi sine theta, and then z is equal to rho cosine phi. Okay, so remember, when we're doing the parametric surface, what we're trying to do is we're not trying to rewrite this in terms of 3 variables. I want to eliminate a variable. Okay, so, well, what do I know? I know that here this is the top half of a sphere with a radius of 2. So that means here rho is just going to be 2. So in each of these, I can describe this surface just like this. So if I write this as a vector function, I have r of u and v. So this is going to be phi, and this is going to be theta. Okay, and I'm just doing this so that way we can keep the same notation that I've been doing. Okay, so this is going to be the x component, so that's 2 sine phi cosine theta I plus 2 sine theta sine phi j plus 2 cosine theta k. Alright, so this describes my surface in terms of u and v. Now, what are the bounds on um, phi and theta? Well, here I know that phi, it goes from, it starts at 0 and it keeps going. So remember, this phi starts in the vertical. It's going to go from 0 to pi over 2, right? It kind of just sweeps out this area, from vertical to horizontal, like this. And then theta, we know that this is going to be revolved all the way around this slice that phi carves out. It's going to be revolved all the way around the z-axis. This is my z-axis. So I'm going to have 0 less than or equal to theta less than or equal to 2 pi. Okay, so what I've done is I've just parameterized, not phi and theta. This is u. I did this whole thing in terms of phi and theta. I want it in terms of u and v. Again, it really doesn't make that big of a difference, but I'm trying to keep this very consistent so things don't get confusing. So phi theta, so that's u, v, u, v, and phi, which is u. Okay, so now I compute the derivatives. So the derivative of this with respect to u, um, and this is going to be So derivative of sine is cosine. Uh, Cosine v. Derivative of sine is cosine. So that's 2 cosine u cosine v j. And then derivative of cosine is negative sine. So 2 sine u. Okay. All right, and then I do the derivative with respect to v. And this is derivative of cosine is negative sine. Sine u sine v. Derivative of sine is cosine, so that's plus, that didn't change, that's supposed to be sine right there. Okay, so derivative of sine is cosine, so this should be plus 2 sine u cosine v, and then this will just be 0, because there's no v component. Okay, and now I do the cross product. Cross d dv. So this is I, j, k, and I have 2 cosine u cosine v. I have 2 cosine u sine v and minus 2 sine u. I'll respace these out. Okay, and then minus 2 sine u sine v, 2 sine u cosine v, and 0. Okay, so I'm doing the cross product of this. And real quick, what this cross product represents is kind of the direction outwards from this surface, right? I'm gonna have u going in this direction, or the RU going in this direction, the RV kind of going perpendicular to that. So when I do the cross product, it's going to be giving me this direction that's kind of outwards to the surface. We'll see why that's useful later, but for now, that's all I need to say about that. Okay, so I do this cross product and I get, so I cross this out and I get 0 plus 4 sine u squared cosine v in the I direction minus, now I cross this out, I get 0 plus, let's see, if it was a, let's see, if it was a cone, would it be similar, but instead of, yes, yes, that is exactly correct. Um, let's see, so here it was, so this is sine u squared. Wait, should I have a negative? Oh, this is 0 minus, that's plus. I have 0, this should be negative. So I have minus 4 sine u squared sine v. And then if I cross out k, what do I have? I have plus 4 sine u cosine u cosine v squared. And then minus, and then I have a minus, so that's going to be plus 4 sine u sine v squared. Okay, just cram it in at the end. Because this is going to simplify. Um, so this becomes, this term right here becomes, it can simplify quite a bit. So this, I'm going to have 4 sine squared u cosine v I plus 4 sine squared u sine v j plus 4, actually, no, let me just put it this way. Sine u, or 2 sine u cosine u, that's going to be 2, that's going to be 2 sine of 2u. Okay. Right, so I have cosine squared plus sine squared, that's going to be 1. And then I have the sine u cosine u, so I just simplify that into 2 sine u. Okay, so finally I want a norm of this vector. So that's going to be so real quick, let me just explain what I just wrote. So here I did the r, the derivative of r with respect to u. So a lot of times in engineering applications, they'll differentiate, say, the u component of this vector versus the derivative with respect to u. They'll usually put a little comma like this to mean the derivative. So that's just something useful to see. Um, so you could have something like fx comma x, and this would mean the x component, the derivative of the x component with respect to x. Okay, but still we're gonna square each of these. So I have, did I want to do that? I don't know if I wanted to do that. You know, let me put that back just in case I don't want to do that. Okay, so it looks like I might have something canceling out nicer if I don't put it as sine of 2u. Okay, so here I have 16 sine to the 4 cosine squared v, this is u, plus 16 sine to the 4 u sine squared v plus 16 sine squared u cosine squared u. Okay, so let's see, how can this simplify? So here I have cosine squared v, sine squared v. If I add those together, also I can factor out the 16. So that comes out, I get a 4 out in front. And here I'm just left with sine to the 4 u plus sine squared u cosine squared u. I see. Here I can factor out sine squared, and I get 4 sines, I factor out sine squared, take that out of the square root, so I get sine u, square root, what's left, sine squared u plus cosine squared u. which is 1. Okay, so that's honestly most of the work is coming up with this right here, the norm of this vector right here. Now I go back up, and this is what I want to integrate: x squared z plus y squared z. Okay, so what I want to integrate is integral over my surface of x squared z plus y squared z d ds. So this is going to become the integral from, so we said that u goes from 0 to pi over 2, theta or v goes from 0 to 2 pi, x we know is, x is going to be, actually let me just rewrite this. Oh, I want it in terms of u and v. So u is going to be 2 sine u cosine v times z, which is 2 cosine u, plus 2 sine u sine v squared, and then 2 cosine u. ds right here, this is going to change to being this vector that we calculated, dA. So all of this right here, I need to multiply that by 4 sine u d phi d theta, or sorry, du dv. Um, okay, so this right here kind of serves the purpose of the Jacobian. Okay, so this is kind of the analog of the Jacobian. So we don't need to calculate that separately. And another point I want to make is this is not necessarily the same as converting this into spherical coordinates. In this case, it was pretty much the same, but the point of converting it into these coordinates was to eliminate a variable. Whereas before, when we were converting into spherical coordinates, we had 3 variables before, and we have 3 variables afterwards. Okay, so here we're trying to eliminate a variable, and that was easy to do if I used something like spherical coordinates. Okay, I can simplify this a bit. So how can I simplify this? So I have integral from 0 to 2 pi, integral 0 to pi over 2. So here I'm going to have sines, it's going to be 4 times 2, which is 8. Actually, hold on. So this whole thing is multiplied by 4 sine u. I'm going to move that 4 way out here in front. So now I'm going to have this. I'm going to have 8 sine squared u cosine squared v cosine u plus, same thing, 8 sine squared u cosine squared, or sine squared v And then that's still going to be cosine u. Multiply all that by sine u du dv. Okay, and now here I have cosine squared v and sine squared v, so I can add those together and that's going to cancel out. So I get 8 sine squared u cosine square, just cosine u and sine u. Okay. How do I want to integrate? Okay, so sine u, that's going to be sine cubed. This should be sine cubed. Finally, this looks fairly simple to integrate. So I'm going to integrate this with respect to u first. Actually, it's separable, right? There's no terms that depend on v inside. So this is just going to be, so 8 times 4, that's 32. Integral from 0 to 2 pi dv. Integral from 0 to pi over 2 sine cubed cosine u du. So now this is going to be 2 pi, so I have 64 pi times this. I need to do like a u sub. I'm going to use w since u is already taken. So w equals sine u dw equals cosine of u du. So this becomes the integral. Let's see, at 0 we get 0. At pi over 2 we get 1. This is going to be w cubed dw. And so we integrate that from 0 to 1, we get 1/4. So this is 64 pi over 4, which is 16 pi. Okay, that long example, and actually we could have realized what is the top half, or what is the surface area of the top half of a sphere, right? This the formula for the surface area of a sphere. Let's see. So this has a radius of, sorry, not 4. It has a radius of 2. I got it right over here, so all the calculations are correct. But the surface area, what is this? Surface area of a sphere is 4 pi r squared, right? And if our radius was 2, wait, hold on, I miss 4 pi r squared. So that gives us 16. Hold up, so I got double what I was supposed to. That's not good. Why did I get double? So that goes from 0 to pi over 2. I'm gonna say I have an extra 2 in here somewhere. There's a lot of room for mistake. 16 comes out, that's 4. Those should all be 4s. I think your bounds might be wrong. Yeah. That's also possible. Any suggestion what you think they should be? So I used from 0 to pi over 2 and then from 0 to 2 pi. So pi goes from 0 here to pi over 2, so that gives me this slice. If I take that slice and I rotate it all the way around, that'd be from 0 to 2 pi. Hmm. Oh, you know what? No, 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 no. I'm sorry. That's just a coincidence. That's not the surface area. What I computed is not the surface area. That is completely. That's my bad. There's no reason why that should be 16 pi. Oh, come on. Why is this not scrolling down? Okay, if I was just integrating the function 1, then it would be the surface area, but I'm not. Right? I'm not just integrating 1, I'm integrating x squared z plus y squared z. Okay, so the integral of this function over this surface is 16 pi. The integral of this function over the surface is 16 pi. Okay, if this was 1, if I just had 1 here and I was just integrating ds, or this norm of ru cross rv dA, this would give me the surface area. But I'm not doing that. I'm integrating this function, and um, and so I'm getting something that is surprisingly similar to the surface area. Just it's just a U sub like Cal2, but I use W instead. Okay, any other questions? So how would the bounds look like if it's for a sphere instead of a hemisphere? Yeah, so if it was for a full sphere, um, why is this being so janky? Okay, so if that's for a full sphere, I could take phi and go from 0 right here, right along the vertical, all the way to here. So for a full sphere, you could go from 0 to pi for u, and then take that and rotate it around the z-axis 2 pi degrees. So that'd be from 0 to 2 pi. So u would be from 0 to pi, and v would be from 0 to 2 pi if you were doing a full sphere. Does that make sense, though? Why that's the case? I mean, so in this case, it's a sphere, and it tells me that z is positive. So I made sure to draw that one kind of upwards, just because I want the stuff that's on top. Um, but it's a sphere, so really it doesn't matter which way I draw it. Um, I could have drawn it this way. So if I would have drawn it this way, and again doing a half sphere, I could have said that phi goes from 0 to, let's see if this was z. Oh, no, 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 I'm sorry. That's misleading. I'm not going to do that. How do I know it was on the z axis? Yeah, so it says z is positive, and then phi is always measured as the angle from the z axis. Okay, so wherever the z axis is, that's where phi starts. Okay, so that's integrating a scalar function over a surface. Okay, now we're going to look at integrating a vector function over a surface. Okay, so this is something that they call a flux integral, or sometimes they still call it a surface integral, but it's often also referred to as a flux integral. And also, somebody make sure to comment when if I'm out of time, because I don't know if this example is going to be long either. But what is a flux integral? So I have some surface. Okay, I'm going to draw it. Some weird surface like this. Imagine that this comes up out of the screen, and I have a vector field that's um, kind of going this way. It kind of does whatever. So maybe um, imagine this is like maybe some sort of mesh, and you have water flowing through the mesh. Okay, and I want to know how much water is flowing through the mesh. Okay, so what I'm going to do is I'm going to look at the normal component um, for this surface. Okay, how much of this vector function goes out in the normal direction? So how much of this is actually going away, and how much is actually, kind of staying inside? So the part that's going out is going out in the normal direction. And I want to integrate and figure out how much of this is going out. Okay, this stuff that's going out, we say that that's a flux. Okay, um, so this is usually written as the integral over a surface of f dot ds, where s here is a vector. So what does that mean? So this is similar to our integral of f dot dr, where this was a vector. Remember, this was the same as f dot r prime dt. So really writing it this way was more of a notation thing than anything else. But what this is equal to is this is equal to f dot the normal component um, ds as a scalar, where this right here, actually I can just write that, where ds is equal to ru cross rv dA. Okay, so this is the outward unit normal vector to my surface. So notice that depending on where you are on the surface, it's going to have a different normal. Okay, and how would we compute the normal? Well, the normal is just this. So that's the normal direction, and then I normalize it like this. And this gives me the direction of the outward normal. Okay, so here this tells me that the integral over a surface of f dot ds, if I replace n here and ds, what I end up with is the integral over s of f dot ru cross rv dA. So now, so basically for a vector, for a vector function, instead of having to take the norm and then integrating of this thing, we're just doing the dot product with this vector and then integrating the result. So it's the result of what we do is very similar, but kind of what it means is quite different. Okay, another example, maybe you have a cup filled with maybe like, I don't know, coffee, or a mug filled with coffee. Okay, there's going to be heat on the inside and it's going to be flowing outwards. Okay, so the rate of change of this is going to be, um, you would have something like F is equal to some coefficient gradient of the temperature. Okay, and this would describe kind of the flow of heat across this boundary, the rate at which it's flowing out. So you could figure out how much heat is flowing out of this boundary by integrating this along the surface. Oops. Okay, so let's do an example. Let me find an example. Okay, okay, so here, right, it says this is our vector function, and let's see, this full question says evaluate the surface integral for the given vector field f over the oriented surface. In other words, find the flux of f across S. Okay, so first thing, just like before, we need to parameterize the surface. So what does this look like? It says of the solid half cylinder. So if I'm looking, oops, if I'm looking, if this is the z-axis and this is the y-axis, right, it's going to look like this. But it's kind of good, but it says x is between 0 and 2. So x coming up out of the board, it's going to look exactly the same. So it's kind of like, you know, it's a half cylinder. It's half of a cylinder. Okay, so how do I want to parameterize this? Well, I'll just use so I'll just use phi, and I guess we can just say v is equal to x. So we'll do kind of like we'll basically do cylindrical coordinates, but it's going to be a little bit different. So here we'll have x is equal to, that's going to stay the same. We'll just say that's equal to u. Right, so that's going to be the depth up out of the board. We know that this distance right here is 1, right, so 1. So I can say that y is equal to 1 we'll just go cosine v, and z is equal to sine v, right? So here I have this distance is the cosine, and this distance is the sine. Sorry, other way around. No, that was right, that was right, that was right. Okay, so I can write r of u v is equal to u I plus cosine v j plus sine v k, right? And now I need to do my derivatives. So I have dr du. They're all squared. They're all squared. No, so this isn't the function. This is my surface. So R describes my surface. if I wanted to write the function in terms of u and v, yes, I would square them. So this is the x component squared, and I'll do that, but a little bit later, not yet. Okay, but this describes the points on my surface. Okay, so Ru, it's derivative with respect to u, so that's going to be 1 plus 0 plus 0. Rv is going to be 0. Derivative cosine is negative sine. And derivative sine is cosine. Sine v. Okay, so now I do the cross product to get the normal. Okay, so I have okay, I have 1, 0, 0, 0 minus sine v cosine v. If I cross that out, I can get 0 minus 0. I cross that out and I get cosine v minus 0. It's going to be minus cosine v. And cross this out and I get minus sine v minus 0. Okay, so one thing to notice real quick, the direction of this vector, minus cosine v minus sine v, that's pointing towards the origin, like this. Okay, so this Ru cross Rv is kind of pointing inwards. And that's not what I want. I want it pointing outwards. So right now my normal is pointing that direction. So all of these normal vectors would be pointing like this. That's not what I want. And this is just a fluke from how I picked u and v. If I would have picked them the other way around, it would have been fine. But I need to make sure that these are going in the outwards direction. So I'm going to do the negative of that vector. Okay, so I'm going to do the negative of this vector. So I'm going to have, I'll just write it this way, 0 cosine v sine v. Okay, and I did the negative again, so that way I make sure that it's pointing, I have the outward normal, not the inward normal. Okay, so now I need to rewrite my function in terms of u and v. So I have x squared, y squared plus z squared. So f in terms of u and v, I'll just put it this way, is going to be, so that's x squared, so that's u squared, I, and then we have sine squared, or we have y squared, which is cosine squared v, and then z squared, which is sine squared v. Okay, so now I have, let's see, so this right here is Ru cross Rv. So now if I do f dot Ru cross Rv, I end up with 0 plus cosine cubed v plus sine cubed v. And then that's what I want to integrate. So I want to do the integral. I need to figure out those bounds real quick. of f dot ru cross rv. So that's going to be integral of cosine cubed v plus sine cubed v dv du. So real quick, what are those bounds? Here I had this angle right here. We said this was our v. So v is going to go from 0 all the way around to pi. And then u we said was just the x component, and we have that u goes from 0 to 2. So v goes from am I just going to add the negative in the very end? The negative because of the normal vector, you mean, right? Which negative are you referring to? Yeah. No, I did that right here. Where to go? That's the previous problem. I did it right here. So here we had negative, negative. So that's where I flipped the signs. Um, but yeah, you should also be able to flip the sign at the end. Because instead of measuring the amount, you're just going to get the negative of the amount. Because again, if you think of we have a surface, we have some amount flowing out. Well, if it's not flowing, if we were looking the other direction, instead of flowing out, it would say flowing in. So what is the amount flowing in? Well, that's going to be a negative number. It's going to be the amount flowing out. So the result isn't going to be the same, but we'll get a different number and maybe a different interpretation if we have the inward normal vector. Okay, so real quick, just to finish this up, we have this goes from 0 to pi, and then u goes from 0 to 2. And I'm not actually going to integrate this because cosine cubed and sine cubed, you can integrate them. Just use some basic trig integration, but that's going to be a little bit more complicated in the time that I have. But none of this depends on u, so I can pull this out of the u integral and have integral from 0 to 2 du of this. Okay, and then I could integrate that, and that would be my my flux integral. Okay, and again, what this represents is here, this describes some sort of vector field, and I want to know how much of that vector field is going out across this surface. So I'm kind of adding up the normal components of all of those vectors to figure out what is the total amount of this vector field going out. I'll just throw in one more comment. So if I had, so why is the bound 0 to 0 to pi? Okay, let me go ahead and answer that. So here, v, think of this as like this theta angle. It's not really theta because theta is in the xy plane, but it's going to be similar to that. So we're going to have these vectors, and this angle right here is v. Okay, so v, it's going to start at 0, right? It's going to start here, and it's going to go all the way around to here. So it starts at 0 and goes all the way around to pi. Why did I set x equal to u? So, basically because I was thinking cylindrical coordinates. Okay, I was thinking cylindrical coordinates, and cylindrical coordinates, right? We think of like some cylinder like this, where the x. Let's see, so I have cylinder where the x and y are the round parts, and the z, is kind of just straight, and that stays the same. Now, here I don't have that. I have something on its side, right? So I have um, this looks something like that, and it comes out like this. So in this case, it doesn't make as much sense to use z as the variable that stays the same, right? So I used x as the variable that doesn't change, right? Because this was my x, and the part that was round are the ones that I used for sine theta and cosine theta. That drawing actually came out pretty good. So this is, we just keep non, like the non, hold up, try that again. Yeah, 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 there really wasn't a need to change the variables. I just set it equal to u because we wanted in terms of u and v, but I didn't have to actually transform anything. The coordinate kind of just stays the same. Diego, are you good on the bounds on y 0 to pi? All right, so it is, okay, so it's noon, or it's just about noon. So I'm going to go ahead and cut off the recording now.